Last episode, you learned every major loss function. Your network knows what to minimize. But knowing the destination is not the same as knowing how to get there. That's the optimizer's job.
The optimizer takes the gradient that backprop computed and decides how to update every weight. The simplest version just subtracts the gradient. The best versions are dramatically smarter than that. I'm Mahaz. By the end of this episode, you'll understand SGD, Momentum, RMSProp, Adam, and AdamW from first principles, the update equations, the intuition, and when to use each one. Today, loss landscape, SGD, Momentum, RMSProp, Adam, AdamW, learning rate schedules, training curve comparison, PyTorch code, and a one-table selection guide. The loss landscape, where optimization happens.
Imagine a hilly terrain where the height at any point is the loss value for those weight values. Training is navigating this landscape to find the lowest valley. The gradient tells you which direction is uphill. The optimizer moves you downhill. In high dimensions, this landscape can have flat regions called plateaus, sharp narrow valleys, saddle points, and many local minima. Vanilla gradient descent navigates this blindly, one step at a time, in the steepest downhill direction.
The learning rate controls how large each step is. Too large, you overshoot the valley and diverge. Too small, training takes forever and you get stuck on plateaus. Every optimizer is fundamentally a strategy for navigating this terrain. SGD, stochastic gradient descent, the foundation of all optimizers.
The update rule, W equals W minus learning rate times gradient of L with respect to W. That's it. Subtract a fraction of the gradient from every weight on every step. The learning rate ETA controls the fraction. Stochastic means we don't compute the gradient over the full dataset. That would be too slow. We use a mini batch of typically 32 to 256 samples. The batch gradient is a noisy estimate of the true gradient, but the noise is actually helpful. It helps escape local minima.
SGD's problems. The same learning rate for every parameter. If one parameter's gradient is always large and another's is tiny, SGD either overshoots the first or crawls on the second. It also oscillates badly in narrow valleys. This is why we need better optimizers.
In PyTorch, optim.sgd, with parameters, learning rate, and optional weight decay. SGD is still used for image classification. ResNet training uses SGD. But for most deep learning tasks, Adam is the default.
SGD with momentum, adding memory to gradient descent.
The physics analogy, a ball rolling down a hill. Without momentum, the ball stops the moment the hill flattens. With momentum, the ball carries velocity. It keeps rolling through flat regions and oscillates less in valleys. The update rule, velocity V equals beta times V plus learning rate times gradient. Then weights W equals W minus V. Beta is the momentum coefficient, typically 0.9. It means 90% of the previous velocity is carried forward. Why does momentum help? In a consistent direction, say, always down, the velocity accumulates and steps get larger. In oscillating directions, side to side in a narrow valley, the gradients cancel out, the velocity stays small, and oscillation is dampened. In PyTorch, optim.sgd with momentum equals 0.9. Nesterov momentum is a better variant. It looks ahead before updating. Use Nesterov equals true in PyTorch for a small but consistent improvement.
RMSProp, adaptive learning rates per parameter.
The core idea, parameters with large historical gradients should get smaller learning rates. Parameters with small historical gradients should get larger learning rates. This solves SGD's one-size-fits-all learning rate problem. The update, keep a running average of squared gradients, e.g. squared, equals rho times e.g. squared, plus 1 minus rho times g squared. Then divide the gradient by the square root of e.g. squared plus epsilon. Each parameter effectively has its own adaptive learning rate. Rho is the decay rate, typically 0.9. Epsilon is a small number like 1 times 10 to the power of -8 added for numerical stability. RMSProp was proposed by Geoffrey Hinton in a Coursera lecture. It was never formally published, but became widely used. RMSProp works well for recurrent networks where gradients vary wildly across time steps. In PyTorch, optim.RMSProp, But Adam combines RMSProp's adaptive learning rates with momentum, so in practice, Adam is almost always preferred.
Adam, the default optimizer for almost all deep learning.
Adam stands for Adaptive Moment Estimation. It combines momentum, first moment, with RMSProp's adaptive learning rates, second moment. Both are estimated with exponential moving averages controlled by beta 1 and beta 2. The update: first moment m equals beta 1 times m plus 1 minus beta 1 times g. Second moment v equals beta 2 times v plus 1 minus beta 2 times g squared. Bias corrected: m hat equals m over 1 minus beta 1 to the t. V hat equals v over 1 minus beta 2 to the t. Weight update: w minus eta times m hat over root v hat plus epsilon. The bias correction is important in the early steps when m and v are initialized at 0. Without it, the estimates are biased towards 0, and the learning rate is effectively too small at the start. Default hyperparameters: beta 1 equals 0.9, beta 2 equals 0.999, epsilon equals 1 times 10 to the power of negative 8. Learning rate equals 1 times 10 to the power of negative 3. These defaults work well for almost every task. In PyTorch, optim.atom. Use it for everything until you have a reason not to.
AdamW, the version of Adam that large language models actually use.
The problem with Adam: weight decay is typically implemented by adding a regularization term to the loss, L2 regularization. But in Adam, this regularization gradient gets divided by the adaptive learning rate estimate, which effectively reduces its impact on parameters with large gradients. AdamW fixes this by decoupling weight decay from the gradient update. Instead of adding weight decay to the gradient before the Adam update, it applies weight decay directly to the weights. W equals W times 1 minus eta times lambda, then apply the Adam gradient update separately. Why does this matter? In transformers and LLMs, weight decay is a critical regularization tool. Adam's broken weight decay was a known issue for years before the AdamW paper by Lashalov and Hutter in 2017 fixed it. GPT, BERT, and virtually every modern LLM uses AdamW. In PyTorch, optim.atomw. Typical hyperparameters: learning rate 1 times 10 to the power of negative 4 to 3 times 10 to the power of negative 4. Weight decay 0.01 to 0.1. Use AdamW whenever training transformers or language models. For CNNs and smaller nets, standard Adam is fine.
Learning rate schedules: the final 10% that makes training reliable.
A fixed learning rate is rarely optimal. Early in training, you want a larger rate to make fast progress. Late in training, you want a smaller rate to fine-tune into the minimum. Schedules vary the learning rate over the course of training. Step decay: reduce the learning rate by a factor every n epochs. Simple, predictable, still widely used for image classification. In PyTorch, step LR with step size and gamma. Cosine annealing: the learning rate follows a cosine curve from its initial value down to near 0. Smooth, no sudden drops. Cosine annealing LR in PyTorch, the standard choice for modern training runs. Linear warm-up: start with a very small learning rate and ramp up to the target over the first few thousand steps. Then decay with cosine. Warm-up prevents early instability when the network weights are random and gradients are large. Standard practice for transformer training.
Optimizer comparison: the training curves that tell the story.
On a standard deep learning benchmark with identical setup, SGD converges slowest and needs careful learning rate tuning. SGD with momentum converges faster and is less sensitive to learning rate. Both plateau if the learning rate is not decayed. RMSProp adapts faster than SGD on tasks with varying gradient magnitudes. Adam typically converges fastest in early training due to both momentum and adaptive rates. Adam can sometimes find a slightly worse final solution than well-tuned SGD.
This is the Adam generalization gap. For image classification, carefully tuned SGD with cosine decay can outperform Adam on final test accuracy. But Adam requires far less tuning. For NLP and transformers, Adam and AdamW dominate unconditionally.
Rule of thumb: Use AdamW with cosine decay and linear warmup for any transformer model. Use Adam for general deep learning. Use SGD with momentum and cosine decay only if you're squeezing every last % out of a CNN.
PyTorch implementation, every optimizer and scheduler in code.
Creating optimizers. SGD with momentum is optim.sgd, parameters, LR, momentum 0.9. Adam is optim.atom, parameters, LR 1 times 10 to the power of -3. AdamW is optim.AdamW, parameters, LR 1 times 10 to the power of -4, weight decay 0.01. Adding a scheduler. Create the optimizer first, then create the scheduler wrapping the optimizer. After each epoch, call scheduler.step. Cosine annealing LR needs T-max, the number of training epochs. The training loop with scheduler, optimizer.0grad, forward pass, compute loss, loss.backward, optimizer.step, scheduler.step. The scheduler adjusts the learning rate automatically. Check optimizer.permgroups 0 bracket LR to see the current rate. One important detail, 0 grad before backward, not after. PyTorch accumulates gradients by default. If you forget 0 grad, gradients from the previous batch add to the current batch's gradients and training diverges. This is the most common training bug.
Optimizer selection guide. One table, every use case.
Transformers and LLMs. AdamW with cosine decay and linear warmup. This is not negotiable. It's the result of years of LLM training research. General deep learning, CNNs, MLPs, Adam. Default hyperparameters work 90% of the time. Start here for any new task.
Image classification when squeezing performance. SGD with momentum 0.9, cosine decay. Weight decay 5 times 10 to the power of -4. More tuning required, but can beat Adam on final accuracy.
Reinforcement learning, Adam or RMSProp. RMSProp was the original DQN optimizer. Adam is now standard for most RL algorithms. Fine-tuning pre-trained models. AdamW with very small learning rate. 1 times 10 to the power of -5 to 5 times 10 to the power of -5 to avoid catastrophic forgetting.
Before episode 13, 5 checks.
Check 1. You can write the SGD update rule and explain what the learning rate controls. Check 2. You can write the momentum update equation and explain why momentum helps in narrow valleys. Check 3. You can explain what RMSProp's running average of squared gradients achieves and why it adapts the learning rate per parameter. Check 4. You can write Adam's full update equations including bias correction and explain why bias correction matters. Check 5. You can explain the difference between Adam and AdamW, specifically what's wrong with Adam's weight decay and how AdamW fixes it. 5 checks. All pass. Episode 13. Building your first real network in PyTorch end-to-end. Everything you've learned, forward pass, backprop, loss, optimizer, in one complete working project. Recap. Every optimizer in 1 minute. SGD. Subtract gradient times learning rate. Simple, 1 global LR. Momentum. Accumulate velocity, dampen oscillation, beta equals 0.9. RMSProp. Per parameter adaptive LR via running mean squared gradient. Adam. Momentum plus RMSProp plus bias correction, the default. AdamW. Adam with decoupled weight decay, the standard for transformers and LLMs. Your challenge. Train your EP10 MLP with all 5 optimizers. Same learning rate, same seed. Plot all 5 loss curves. Post which converged fastest. The optimizer is not a detail. Wrong optimizer means slow training, divergence, or a model that never converges. Now you know the mechanics behind every major one. The full training loop is now complete in your head. Architecture, forward pass, loss function, backpropagation, optimizer. Every piece in place. Episode 13 puts them all together. Episode 13. Building your first real end-to-end network in PyTorch, from raw data to trained model to evaluation. Subscribe. Do the challenge. See you in episode 13.